Given by Edgardo Stockmeyer from the Universität München, and his topic is confinement-deconfinement transitions of two-dimensional Dirac particles.
Thank you very much. Thank you very much to the organizers for this very nice meeting here in Cambridge. I will speak about a joint work with Joseph Meringer, who is a student of mine in Munich. Maybe I should apologize because of the date error there, so I'm sorry. So just to fix ideas from the very beginning, I mean, I would like you that we think about a two-dimensional Dirac particle, massless, and this particle is going to be inserted in an electric field, and in an electromagnetic field, V and B, and throughout this talk, we will assume that these electromagnetic fields grow at infinity in all directions. There is an exception, I will tell you, when we don't need to assume that, but for the purpose of imagination, we can start thinking about magnetic fields and electric fields that grow at infinity in all directions. We will not need spherical symmetry. However, we will bring spherical symmetry to discuss some intuitions. So the goal of this talk is to present results on the spectrum of the Dirac operator if you play with the relation of the electric field and the magnetic field at infinity. So playing with the quotient of these two quantities. Okay. So let me first set up the notation. Okay, so you have seen that already. So the Dirac operator is written there. So here, sigma are the Pauli matrices. And I mean, let me observe that these Pauli matrices are two here, so that's a sum, are off diagonal. So this operator is off diagonal and self-adjoint, so can be written like that. dA is equal to 0, d star, d 0. And d and d star are important quantities for the algebraic manipulations with these operators. You can think of them about a creation and annihilation operator. So that would be the creation operator, and that would be the annihilation operator. And they satisfy an important commutation relation. D and D star is equal to 2B, and that is true also when the magnetic field moves. It depends on the position. Okay. So also an interesting remark, as opposed to the Schrödinger case, you can define the full operator, which is going to be called just dA plus V. So A carries the magnetic field, and just plug in a potential. It's going to be a diagonal thing in the Pauli matrices, the potential. And it is self-adjoint. It can be self-adjointly realized without any restriction on the growth of B and the potential V. Okay. Now, let me motivate the discussion here. Just telling you, let's think on the case when B is equal to 0 and the electric potential is spherical symmetric. Okay, let's start thinking on that. Then one can prove, and there are works by Tischmark, Erdelji, and Carl Michael Schmidt, that the spectrum of the operator D0 plus V equals the whole real line and is absolutely continuous. So it contains only scattering states that will go to eventually to infinity. And so I would like to recognize this phenomenon that's saying just that the potentials growing at infinity in the Dirac theory, they have to do with deconfinement. Okay. In fact, you can prove more. I mean, there are some proofs. In 3 dimensions, you can prove, without assuming that the potential is spherical symmetric, that the 0 plus V has no eigenvalues. This question has been addressed by Vogelsang, Kalf, Okai, and Yamada. Okay, so that's when the magnetic field equals 0 and the potential grows. Okay, now let's turn the question. So in the case when V is equal to 0 and you have an electric field, a magnetic field B, which grows at infinity, then you know that the spectrum of the operator is discrete, away from 0. So this has to do with confinement. So you need infinite energy to go to infinity, or the particle needs infinite energy to go to infinity. So this a work on this direction, or a proof of this fact is contained in the paper by Helfer, Norigat, and Wang. And interesting, the zero modes. So the zero modes are special objects here, and so you find infinitely many of those. So the spectrum, let me tell you one more remark. So the spectrum of the Dirac operator with only magnetic field, dA, is symmetric with respect to 0, is discrete in this case away from 0, and 0 is an eigenvalue of infinite multiplicity. And so I could understand that you have a confinement away from the energy zeros. The energy zeros you cannot localize uniformly. Okay, so the goal, what we want to understand is the combination of these two effects and see what happens. Now, to start thinking, let's consider the spherical symmetric case. So if you consider this case, so you can decompose the full operator as a sum of the operators with fixed angular momentum, J. And then the spectrum of the full operator is the union of the spectra of all these little operators, Hj. Okay? Now, there, in order to have spherical symmetry in your Hamiltonian, you can choose a gauge which is also spherical symmetric. That's called the rotational gauge. Is given by this function, 1 over r integral from 0 r b s ds. Okay? Now, it is easy to show that if the value of V is smaller, remember that V has a delocalizing property and the magnetic field has a localizing property. So now if the magnetic field wins at infinity, in this sense, of R is sort of B times R, wins at infinity, then you can easily show that the spectrum of these operators is discrete. Okay, so you have this effect. And if you inverse the inequality, so if the electric potential wins at infinity, is stronger, then Schmidt and Yamada showed that the spectrum of this operator is absolutely continuous on the whole, and is equal to the whole real line. So you have a transition there. You have a transition, so let me plot it like that. If you look at the value of V squared, I will use V squared here for some reason you will understand. If the value of V squared is equal to, at infinity, is smaller than the value of A squared, then you have discrete spectrum, which has to do with confinement. If it goes up, if it's bigger than A squared, then you have deconfinement. Okay. Now this observation, we also found it in a paper by physicists. A recent paper because of the recent interest in graphene. They were very happy with this effect. They were saying maybe with this effect we can find a device to localize and delocalize particles in graphene by manipulating the fields very far away from where the sample is. Okay, fine. Now, here comes the question. So, clearly, if you have an absolutely continuous spectrum and you are in this case where the electric field is bigger than A, then you will find that the spectrum of the full operator is absolutely continuous. So it's delocalizing. However, if you have that the potential is smaller than the magnetic field at infinity, you don't in general find that the spectrum of dA plus V is discrete. You don't find it indeed. In fact, maybe it will be discrete if the spectrum, if V squared is very small compared with A squared. It's very weak. But maybe there is a transition here where the spectral points can start accumulating and you create some type of essential spectrum. An essential spectrum is, of course, a weaker form of localization than discrete spectrum, because you can find states which are localized at infinity, which reach those energies where the spectral points accumulate. Okay, so this is the thing. I hope you have the picture. You sum up these discrete spectra, and then at some point one expects to find accumulation points, and therefore some transition from the confinement to deconfinement. So the first theorem is the following. So I would like to write out the conditions because I'm going to use that in a minute. So the first condition is that b of x goes to infinity at infinity. And the second condition is that we can control the derivative of b by b at infinity. And in fact, this goes to 0. Now, this is not so crazy. What we are asking for is some sub-exponential growth of b. Okay? And the third condition is that the limit, maybe the limit sup of b squared divided by 2b is strictly smaller than 1. Okay? If you have that, then we can show, we will see the proof, we can show that the spectrum is discrete. So which means actually what we talk about, that if b is small compared with 2b, then we expect to find discrete spectrum. Okay? Now let me remark that a similar result was proven by Suzuki in 2000. However, they got awards bound for the limit behavior of b squared divided by 2b, so they proved, say, until here, that the spectrum is discrete. Okay? And the nice thing about this theorem is that it's in fact sharp, in the sense that potentials that satisfy conditions 1 and 2, but go to 1 at infinity, we can find that there is a creation of essential spectrum at this point. Okay? I mean, it is sharp not in absolute terms. We will have to ask, this goes to 1, but goes to 1 with some velocity. Okay? But that's, I think, a technical assumption. Okay, let me show you more precise statement. Sorry. Now, let's go back to the spherical symmetric case and think that b goes like x to the power s, just to fix ideas. So if b goes to like x to the power s, then a goes like x to the power s plus 1, and the square goes like that. Okay? So the transition is here, is in this power. It's from the power s to the power 2s plus 2. From here, in the spherical symmetric case, we have absolutely continuous spectrum. From here, discrete, and as I promised, this is sharp. So here is the result on sharpness. We have an additional assumption on the regularity of b. Okay? But it is just the same assumption. So satisfying 1 and 2, we can be a little bit more general with 2, and we need that b squared divided by 2b goes to 1, but with certain velocity, given in terms of the electric potential. Then in that case, we can show that the essential spectrum of dA plus v is non-zero. So we find, boom, essential spectrum here, right there. Okay, now of course, the question is what happens in between. Okay, so so what happens in between is given by the following theorem. Here is some technical requirement. I mean, we will ask some functions to vary regularly at infinity, in the sense that if you have a function which goes to 0 when you divide by x, or goes like O of 1 or O of x at infinity, then this quotient here is bounded by a constant. And you can think that this is again not such a crazy assumption, because it is, for example, satisfied when the f has a power law growing or so. Okay, just imagine that f is equal to x to some power, and that works. Okay, so we have this assumption. In any case, here is the theorem. It's a little bit full of conditions and so on, but they are easy to understand. So let me try to walk you through them. Okay, so here is the theorem. We will assume that b and b are continuous functions, that the gradient of the potential n of the magnetic field vary regularly at infinity. That is this condition. And we would like that there is a path, a continuous path that goes from some point on to infinity, such that the following conditions are satisfied along the path. So the theorem asks for conditions only along a path which ends at infinity. So which are those conditions? we will ask that v squared divided by 2b goes to infinity. Okay? Now, if you remember the condition we had before, it was v squared, the sharpness was v squared divided by 2b equal to 1. So we went a little bit up. Yeah? We jump. We will ask that v squared divided by 2b goes along this path to infinity. But it should not go very fast. This means that v squared has to be big with respect to the magnetic field, but not too much. This is reflected in these two conditions. Think again in the polynomial thing. So gradient of b divided by b goes like 1 over x. And so the growth of b squared divided by 2b has to be at most of 1 power. Okay, 1 power x. That is what this is telling you. Here is again the same thing if you think of power law, on the power law. Now there are technical assumptions. I mean, we want that b0 is bigger than some constant, and it also grows. I mean that you can find a k such that b is smaller than this object b squared divided by 2b that goes already to infinity. I mean that's okay. And then we ask that the v has a super logarithmic growth. Okay, so that's that. And then the statement is that the spectrum of the operator is essential and is equal to the full real line. Okay. So now, if we assume, or if we go back to the spherical symmetric case, and b is equal to x to the power s, we know already that here there was discrete spectrum from the spheric operators, and then what we find is actually that between these two powers, remember I need that v squared at infinity has a bit more of growth than 2b, such that this object goes to infinity, but it cannot grow very fast. It can grow only 1 power more than 2b. That's that here. And on this interval, we find a dense pure point spectrum. I mean, everybody touched everybody. And here we don't know what happened, and here we don't know what happened. Okay? So that's that. That's the result. Are there questions? Because now we can turn for the proofs. Okay. So, so the proofs, we want to prove that the spectrum is discrete, and it is sufficient to show that you can have such an inequality, that dA plus V can be bounded by a constant time V. This tells you that a localized particle, if it goes to infinity, it needs to pay infinite energy because V grows. Now what we do, we cut the potential. We can cut it because, I mean, we are talking about essential spectrum or discrete spectrum in this case. And so we can cut the potential and arrange it in this way. So we will assume that V of x is bigger or equal than 1 over delta for all r, that the gradient divided by V is smaller than delta, and delta can be chosen arbitrarily. And since V squared divided by 2B is in lim sup strictly smaller than 1, then we can find an eta that does this job, that represents somehow the lim sup. So we can simplify the problem, and the advantage of that is that we find a small parameter we can play with. Okay. Now here I would like to draw a picture. So we have to play with dA and with V, and and so what we find that the spectrum of dA, in this case, under these assumptions, with the new magnetic field, should look like that. You have, again, because you have growth, infinite flux of magnetic field, you find that the zero modes are infinitely degenerated. And then you have a big gap, which is of order 1 over delta squared, I think, 1 over delta. So a big gap where the rest of the spectrum is situated. And here you only have discrete spectrum. Okay? So the reasonable thing to do in this case is to split the problem, what is going on here on the zero modes, and so on this part of the space, which is represented by a projection, P0, and what is going on outside, which is represented by an orthogonal projection which is equal to 1 minus p0. Okay, so that's what we do. We split the problem and see, and I mean start binding or bounding from below. I think I explained all that. Yeah. Okay, so once you split things, then I mean you have to work that out. Of course, you have to use that p0 when dA is p0, then it's equal to 0, and so on, and you find this ugly expression. But there are two green expressions here, which are sort of the cross terms, and those cross terms we can estimate them. And why we can estimate is because of the fact, well, one of the reasons because we have this small parameter, and we have this big distance. So we can control very good these guys. And this is represented in this lemma, which controls commutators between the projection onto the zero space, and when you apply the Dirac operator, and even when you apply the electric potential, you get small quantities. Okay. Also here. So with this, with these two estimates, we can just forget the two green terms. This gives us order of delta squared. Okay, this gives us 1 plus an order of delta squared. Now, the good guy here, I want that to be positive. The good guy here is this one. Okay. So if you put all these estimates together, what you get is that this operator is bigger or equal than this object plus delta times the good guy with an error of delta squared. Okay. So what we have to show is that this guy, so it's dA p0 orthogonal phi squared minus a constant which is almost 1, and dp0 orthogonal phi squared is bigger or equal than 0. So we will use that b squared is smaller than 2b. Also, that's globally because with cut potential we can do it. And we want to show this inequality. Now we write that down using the creation annihilation operators. And we will use the symmetry of these operators. So if you remember that dA is equal to 0, d star d0. Okay, and so we plug that in, and we get a matrix. And the matrix is projected. I mean, that's the projection away from the 0 modes. So the first observation is that because of this commutation relation, we can immediately see that dd star is bigger or equal than the magnetic field, than 2b. So that's dd star is here. So that's bigger or equal than 2b, and b squared is smaller than 2b, and so we can control very well the lower term. Okay. Now for the upper term, you see here, and you can also see that d star d is of course smaller than dd star. But on the other hand, we know that those two operators are isospectral away from 0. And we are sort of away from 0. Okay? And so how to do that is, I mean, we find a unitary transform which has the property that from d star d you go to dd star. And dd star is the guy we want to have because he can control easily the b squared. Okay? Then we will repeat the problem we had here below. So we apply this transformation to the term here above, and then what we find, we can right now, we can flip from d star d to dd star minus c times d. There is, what is, this s is, this s shouldn't be there. So, sorry, the s shouldn't be there. Minus c of delta v and times this object here and b again. Now, if you remember what I tell you here before and how we control the lower term, you see that if we can show that lambda, I mean, if lambda was 0, then we are fine because it is the same problem. So what we have to do is to show that lambda is small. So what do? We use that this S star actually can be represented to the sign of dA d0. This formula is, of course, valid away from the kernel of dA, which is the place where we are. You cannot divide by dA otherwise. Okay? So using this formula, you can transform this problem to a problem of commutators of dA, and this you can solve using functional calculus. Okay? So we find that this commutator is of order delta squared, and that gives us exactly that the norm of the commutator written here is of order delta squared, and we are done. So that's the idea for this problem. Okay, so now let's show that the result is sharp. So what happens when this b squared divided by 2b goes to 1 at infinity? Okay, so I put it here in the title. So this is what we have. We have that b squared divided by 2b minus 1 is small at infinity in some sense. And we want to show that the essential spectrum is non-zero. So it is enough to find a space which is infinite dimensional such that this inequality is fulfilled, such that the energy is smaller than a constant for infinitely many states. So that's exactly, this should be an accumulation point there in between. Now from where are we going to construct these wave functions? From the zero modes. They are not directly the zero modes, but they give us the source to construct the functions phi. So we know that since b is growing at infinity, then we have infinitely many zero modes. So that's a source to get a lot of functions. And we know them very explicitly, by the way. I should have mentioned that. Okay? So now the space we are going to define to do the job, it looks a little bit odd, but I mean, they are two spinors functions, and the upper component is the creation operator applied to the zero modes. So it's like you go up in the Landau level. And the lower component is going to be minus b times a zero mode. So we define this, the space of this type of vectors where omega is an element of the kernel of d star t, which is infinite dimensional. One has to show that this kernel, that this space is also infinite dimensional. There is where we use these funny conditions, funny extra condition we had. Okay, so what do we have? We have the space, we have the dimension, and now observe what happened with these guys. So how is the norm of the vectors here in W? So d star omega squared is equal to this, and now use the commutation relation. You can flip them and have a 2b. This guy is here, but when you flip them, you use the fact that d applied to omega equals 0. So you just get the magnetic field. And so the norm of d star omega is equal to the square root of the 2b, and this is about b omega squared. So which means that if you pick a vector from this space of this form, then the norm of this vector is about the norm of b times omega, because upper and lower component have the same type of norm, the same type of energy. And now it's an algebraic situation. So we apply this operator to this test function here. So if you apply b times d star minus b, here we have a commutator, d star b minus b squared. Now again, we use the commutation relation to write that d star applied on the zero modes is actually equal to 2b. And the commutator, we can write it like that. It's a commutator b and d star divided by b. This commutator is like the gradient of b, and the gradient of b we can control by the potential itself. And here again, I mean, we have something which is small, because 2b or b the quotient b squared divided by 2b, this goes to 1 as x goes to infinity. And so that's, I mean, then we are there. I mean, we have to just compute this norm. This is bounded by the some constant. This constant comes from here. Some constant times the potential applied on the zero modes, and this is about the norm of psi here. And so we are done. Okay, so now for the proof of the case with the proof of the next theorem, I wrote down the theorem, so here is the result. I will tell you why it works. Okay, so let me erase the blackboard. So I don't know, maybe I will need the two blackboards. So why I mean, I want to convince you that that works, and that's that. I'm not going to go into details in the proof. This proof is technical, but the idea is nice and not so complicated to explain, okay? So what we need to prove, so that dA plus B, we need to find a sequence psi n such that this thing goes to 0. I will send this the energy 0, but I promise you you can do exactly the same for B minus E. That's what we want to prove, and the reason is because the potential grows and then E is not an important thing. So that's what we want to show, to find psi n. What do we have? The first condition there tell us that we have a path. We have a path, and along this path, the limit of b squared divided by 2b goes to infinity at infinity. Okay, and here is the observation. Then we find a sequence of points on the path such that b squared at the points xn is equal, or if you want, divided by 2b of xn is equal to n. Okay, this is because thing grows and you start at some point, it's finite, and then it has to go to infinity. Everything is continuous. So and the thing is that, so which means that b squared is equal. Let me write it. So b squared, I will write b squared index n is equal to 2n times bn on these points. Now this 2nbn is equal to the square of the nth Landau level of the problem with homogeneous magnetic field Bn. Here we don't have homogeneous magnetic field, but we can imagine that the magnetic field is locally flat. Okay, so on these points we have magnetic fields Bn minus 1, Bn, and Bn plus 1. And this object here, 2n Bn, is equal to the square of the nth Landau level associated to the problem homogeneous magnetic field equals to Bn. Square of that. And as we just discussed, the spectrum of the magnetic Dirac operator is symmetric with respect to 0. So you can find positive and also the negative energy. For each positive, you find exactly the negative energy to it. Okay? Now, associated to each of these energies, so we have, you see, we have for each point a magnetic field. For each magnetic field, we find an nth Landau level, and for each one of those, we can set up some function. So associated to them, we find the functions which solve the problem, the homogeneous problem. And these functions are very, very localized because we have a magnetic field, and it's a very high magnetic field. And these functions are Gaussian localized. I will ask these functions. So from here, we will cook up the Weyl sequences. So we will ask these functions to satisfy the equation dAn. I tell you in a minute what is an, phi n, equal to the square root. As I told you that this number is the square of the energy given by the Landau levels. So equal to minus 2n Bn phi n. Okay, so these functions, when you apply the operator d(an), I'm sorry, I should tell you what is d(an). An is here the magnetic vector potential associated to these magnetic fields, which are numbers. It is the value of the magnetic field at those points. Okay, so An is then equal to 1/2 Bn x minus xn. Okay, and we will ask those functions phi n to give you the value minus the square root of 2n Bn. Why does it work? because of the localization. So you have these points again, and associated to it we have a Landau eigenfunction, which is very localized because we have high fields. So associated to it we have a very localized eigenfunction here, and the fact is, so the way we cook the Weyl sequence is given by something like that. So we need a gauge, which this is a technical thing, is just to center the gauge at each of these points. And then the eigenfunctions we just discussed. And then we need to put always a localization function. But to put a localization function here is very cheap. Yeah? It costs very little because these functions are very localized already. Okay? And so when you plug the operator dA plus V on this function, the fact that you have this phase, what it gives you is it centers the gauge at these points. So I'm allowed to write here dAn. I will gain an error. And then this is the object I want to apply to this phi n. Okay? As I told you, I can forget this localization for the moment because it's cheap. Okay? And then you see it. When you apply dAn to phi n, then you get minus the square root of 2Bn n. And when you apply V, because these guys are very steeply localized, then what you get is actually dAn plus the value of V at the point xn. So it's almost like a delta function. It extracts you the value. Again, you gain an error. And this error you can control using the conditions we have, and the main property here is the localization of those functions. So that's what I wanted to say. Thank you very much.
Yeah, thank you very much. Are there any questions or comments?
Why do we need a path?
Yeah, because, I don't know. We haven't written it down, first of all. It might change this thing with the path or a sequence. You say you can have a sequence. See, the thing is, if we put the conditions here for a sequence of points, the problem is that we need not only to do that for dA plus V, but also for dA plus B plus minus E. And then the points of intersection we find may change. And so you will need it. So that's the way. I think you can repair it using the the regularity and so on, but we haven't done that yet. So you don't need a path. I don't think so.
Yeah. So can you explain what is the mechanism which gives that in the absence of the magnetic field and with the radial field?
It's exactly what Florian explained yesterday. Yeah? Florian explained that when a particle, then a Dirac particle goes through a barrier, then the barrier is transparent if you hit the particle in a perpendicular way. If you hit the barrier in a perpendicular way.
Mathematically?
Mathematically. Well, mathematically you can see it very easily in one dimension. Because you can, to convince yourself feeling-wise, you just solve the equation asymptotically for R very big and you find oscillatory solutions. I mean, we can do it. It's okay.
Well, if there are no further questions, then let's close the session and thank the speaker again.